last left Family Size VM, I was working through a CPU test suite, implementing each new instruction as it occurred. I ended up 1,000 steps in out of 9,000. I increased the font size to make it easier for you to see. This made it a bit harder to move around the file because less would fit vertically on my screen. So I started sorting the opcodes into 4 groups based on the 2 least significant bits. Group 0 has miscellaneous instructions for loops, branches, and the like. Group 1 has most of the instructions that do arithmetic. Group 2 has read, modify, write instructions, such as adding 1 to a variable. There is a Group 3, but they're all unofficial. I remembered to rerun the test several times while sorting to make sure I didn't break anything. After a brief tidying, I returned to the bit shifting instructions that I was working on yesterday. Most of Group 1 has a pattern: operation in bits 5, 6, and 7, and addressing mode in bits 2, 3, and 4. The addressing mode is how the CPU finds the operand in memory. I decided to pre-process 49 of the Group 1 opcodes so that I'd only have to implement 1 of the 8 for each operation. 2 addressing modes on the 6502 have page crossing penalties. If adding the offset to the base address carries into the upper 8 bits, it spends an extra cycle reading an address that's 256 bytes too low. An acceptable sacrifice to fit an 8-bit processor on a die that small. I encapsulated this penalty into a function. Pre-processing made a few opcodes redundant, letting me delete them. Uh-oh, hit a regression. All taken care of. The preprocessor didn't apply to store instructions for 2 reasons. Their indexing penalty is different, and immediate mode makes no sense. So I needed to fill in all the modes for the stores by myself. I mentioned read, modify, write instructions earlier. These opcodes in Group 2 are for changing the value in a RAM address without affecting the values in the processor registers. They can shift a value by 1 bit or add or subtract 1, and they can probably share the same logic as Group 1 stores. A store preprocessor would help too. I started by describing the opcode bit patterns that the store preprocessor should handle. Sometimes I draft short snippets outside the main source code file so that I don't get distracted. The address calculation was similar to load, though not quite the same because it gave a destination address, not a value by itself, and stores that can have a page crossing penalty always have it. I was up to 2,000 steps with the nest test log, an improvement of 1,000 in an hour. My ThinkPad's lithium-ion battery was very low. A new battery that I bought had just arrived in the mail. It needed to be calibrated to let the system know the charge capacity. I did this by running it on battery to 5% and then plugging it in to charge to 100% twice. While it was charging, I sought to finish the preprocessor and progress in nest test to 3,000 if not 4. The preprocessor, once finished, would let me delete Group 1 stores. I reused those parts of the load preprocessor that made sense. I needed to debug the addresses making it into the preprocessor. Once I did, I could start writing the 6 official read, modify, writes. Here we go. With those out of the way, I was up to 3,000. There was still 1 store that was acting up. An indexed write was wrapping around the end of memory back to the beginning. MOS's original 6502 has a bug. The indirect jump, used with function pointer stored in RAM, does not carry when advancing from the low byte to the high byte. It's fixed in the later 65C02 and 65816 processors, used in the Apple IIc, Enhanced 2E, and 2GS, as well as the PC Engine, Lynx, and Super NES. On the NES, however, I had to emulate the bug, and it got me to 3,500. Boom! 4,000. Might I finish all official opcodes today? Yep, with time to spare for adding more unofficial no operations. 5,260. That's almost a mile. I could say I've now walked a mile in an emulator developer's shoes. But do gloves even count as shoes? One problem with store preprocessing was left for tomorrow. I don't really need to support unofficial opcodes that games don't use. It just happens to be more convenient to pass all of the test suite, and a few more obscure games use opcodes on the list, such as Puzznic and Supercars and the Streamers remake. The unofficial opcodes might be considered bugs in the 6502. However, not all opcodes in the family behave the same way. Even the bugs have bugs. This meant I had to make some of them without the preprocessor. I could still use my functions though, including making a new one. Many unofficial opcodes combine two different opcodes. For example, SAX combines store register A and store register X. Because 0 is stronger than 1 in NMOS circuits, it stores the logical AND of the values in A and X. These 6 instructions, each of which has 7 addressing modes, perform a read, modify, write on an address, and then do the arithmetic operation from the same row with the same value. The store preprocessing should work on these. I began by copying and pasting the read, modify, write implementations. I verified that preprocessing was indeed going. In 39 minutes, I'd done half of the remaining unofficial opcodes, and the rest 3 minutes later once I had the right approach. After doing a CPU in a total of 5 hours and before I started on graphics, I cleaned up the structure of my test harness. I started by splitting things out to separate source code files. First the definition of the ROM header, then the definition of the CPU registers, then prototypes for the CPU's public interface. I took an opportunity to mark private functions as static. The compiler has more leeway when optimizing a static function. It can copy parts of the function inline into its callers, and it doesn't have to obey the platform's calling convention. This gave me an opportunity to move header parsing to its own file. A quick check to make sure everything still worked before I moved the CPU to its own file as well. And it still worked. In addition to the 9000 step mode, NestTest has an interactive mode. It draws a menu and lets the user select a subset of tests to run. To use that, I'll need to build a picture processing unit, or PPU. The PPU accepts commands from the CPU to fill video memory and generates a 240-line composite video signal to send to the TV. Every NES game starts by waiting for the PPU to become ready. If there's no PPU, a game just spins in an infinite loop. This meant I needed to at least count the dots that the PPU draws to let the CPU know where each video frame starts and ends. The NestTest log tells me how many cycles each instruction uses and how many PPU dots that amounts to. On most consoles, the PPU generates 3 dots during each CPU cycle. That differs in Western Europe and Australia. Let's see if I can match the timing for the 9000 steps of NestTest. In this emulator, the CPU runs all the timing. This means it tells the PPU to calculate dots. That's obviously not how the real console works, but in emulation, all I care about is that it behaves as if it did. Ugh! As if! I added the PPU registers to the system's register file. I needed to keep in mind alignment, where 16-bit variables should start on a 2-byte boundary and 32-bit variables should start on a 4-byte boundary. If I order the fields in the struct properly, the compiler won't have to add useless padding to ensure alignment. Once I added fields, I needed to initialize them, either at power on or when the reset button is pressed. Time to count dots, turning status flags on and off, and give the CPU a way to tell the PPU what to do. Like the CPU has its own data bus going out to the CPU. It has some of the same open bus behavior as the CPU's data bus because long metal traces in the PPU behave as capacitors. These hold data for at least a few milliseconds. Reading PPU status charges some but not all lines of the bus. In older PPUs, the palette and object positions are write-only. Later revisions let the CPU read those back, probably for testing. Micro Machines, an unlicensed game by Codemasters, ended up depending on snooping the object processing this way. Some of its menu screens subtly misbehave on the older PPU, and Japanese units are more likely to have an older PPU. Normally, the PPU lets the CPU read and write video memory either during the vertical blanking period between frames or on a fully blank screen. Reading outside these times creates unintended behavior such as skipping lines of the background. I called some of these behaviors pathological during development. The PPU maps its palette memory on top of the end of video memory. The PPU has an internal pointer in video memory. Reading or writing video memory adds either 1 or 32 to this pointer, depending on the setting of another control register, which meant I had to define the bits of that register. Data read back from video memory has a 1-byte delay. The PPU returns the most recently read byte and then reads another. This way the video memory doesn't have to be quite as fast as the CPU. I made my first draft compile. I figured I'd sketch how palette writing works. The palette has 28 bytes, of which 25 are actually used during rendering. Palette bytes at indices 16, 20, 24, and 28 don't actually exist. Writing to them actually writes to index 0, 4, 8, or 12. This mirroring saves a small amount of space on the PPU silicon. I just spent 24 minutes on PPU things other than counting dots. Once I realized how sidetracked I got, I went back and added a check that it was on the same dot as in the log. And it worked the first time. Each frame ends with a vertical blanking interval, vblank for short. During this period, video memory is open for writes. The PPU can notify the CPU that vblank has begun. This causes the CPU to interrupt what it's doing and jump to code meant to run during vblank. When handling an interrupt, the CPU doesn't read the operand. Instead, it forces itself into a variant of the break instruction. This instruction pushes the program counter as if calling a subroutine, pushes the processor status flags, and jumps through a vector near the end of memory. No time to test the break handler today. See you tomorrow!